Hello, I'm Channa Bankapur. I'm going to discuss my solution to the LeetCode problem sliding window maximum. It's today's daily challenge in LeetCode. The problem definition is we have an array of integers and a positive integer k. Consider a window of size k, which is a range of contiguous k elements. So the first window is going to be from the first k elements in the array. When we slide the window by one position, which is essentially considering the k elements starting at index 1. So we need to find the maximum of every window starting from very left and slide the window towards the right and to the very right. So we need to return that array of maximum elements. Uh, let's consider this example to understand the problem better. There are 8 elements and k equal to 3. So the first window is going to be the first 3 elements of the array, and the max of that is 3, which is noted here. And when you slide the window by one position, we consider the next 3 elements starting at index 1. The max is again 3. And when you slide the window again, the max is 5. And so on. The last window is going to be the last 3 elements. The max of that is going to be 7. So we need to return this array of max of every window, right? So there are multiple ways of solving this problem. I'm going to discuss two methods. One is very easy and it takes big O of n log k time, which still works in big O of k extra space. And I'm going to discuss another tricky method which is going to work in big O of n time and then big O of k space, right? So let me discuss both of these methods with my code directly. That's easier for us to understand. So the first method is I'm using a balanced BST here, which is a balanced BST is either an AVL tree or a red black tree. In C++, I'm using a multiset. So multiset is a balanced BST which uses only keys. There are no values there. It's only keys, and there could be multiple occurrences of keys, right? There could be duplicate keys. So that's what I'm using in C++ here. And the idea is very simple. So the first window is going to be the first k elements. I'm going to insert all of them into the BST here. And finding the max in a BST is very easy. So it's going to be at the end of end of it's going to be at the end. So R begin iterator is going to give me that. So that is the first result I'm going to note. And in the for loop, every time I'm going to slide the window by one position, and I is going to be the last index of the window I'm considering. So sliding the window needs these two steps. I'm going to remove the element at the beginning of the current window, which is at nums of I minus k, and the new element is at nums of I, which is when I insert into the BST. Essentially, we have a new window here, and max of the window is still available at this place, right? So that's how I'm going to construct this. And if you look at the time it takes, we have these three operations: find, erase, and insert. All of them take big O of log n time, or say big O of log k time, because there are only k elements in the BST, and this runs for linear number of times. That's why the overall time it takes is big O of n log k, right? And space wise, we need a BST which can hold k elements. That's why it is only big O of k extra space, right? So it looks good, but yeah, because of BST and big of n log k, it takes little more time, but it is still acceptable, right? It accepted. Let me show how much time it takes. It took more than a second, 1312 milliseconds. And if I look at among C++ submissions, it is beyond the window here. So that means less than probably 1% of the people got this much of time. And even space wise, it took 166 MB. And if you look at the window here, it is only up to 165 MB here. So space wise also it takes actually a lot more space than other implementations, right? So let me discuss a more efficient method. The efficient method is a little trickier here. So let me explain the logic. This is the code, but I think it's not easy to read. So let me explain the logic. So the whole, all the n elements from say 0 to n minus 1, I'm going to split them into windows of size k, right? Actually blocks of size k. Suppose if k is equal to 10, so I'm going to have say the first 0 to 9 are going to be the first window or first block, and the second block is from say 10 to 19, and third block is going to be from 20 to 29, and so on. right? The last block could be less than or equal to k number of elements there. All right. So let's see how is this block helpful. Let me consider some window in between. Suppose the window starts at say 13 here and then ends at say 22. So this is a window of size 10, which is of size k, right? So the way I separated the blocks is I'm going to find the max of this set of elements in this block, the block which is starting at 13 and ending at 19. So somehow if I know the max of this one without really iterating through this, and also know the max of the in the next block starting from 20 up to this no, index 22. If I know these two max, there are 7 elements here and the 3 elements here, then the max of these two is going to be my answer, right? So this is the idea I'm using here. But how do I compute something like this? Do I have to pre-compute everything in one shot, or can I do it on the fly? So this I'm going to call it as the max of the 3 elements in the new block is max up to, right? Max up to can be computed as we actually keep moving the window, right? If the window is at I, so this is at I plus k minus 1. So that element I keep considering and max, you can find it. But also I need to reset the max whenever I hit the new block. So every block starts at I mod k equal to 0. If I mod k is equal to 0, that means this is a new block, right? So I'm going to start the new max up to as a new from starting from this point. But we need something like this: the max of the last 7 elements in this one in the previous block, right? So this is actually a little trickier. We cannot actually do it on the fly while we are going from left to right. So what we need is, so because when I'm at say at position I here, in this case I is say 13, I need to find the max of the elements from 13 to 19. So that should be pre-computed, but it's only one block. I don't need to compute everything in one shot, right? So let's see how do we do that in the code. That should be easier to understand. Now here, look at this. I'm finding max from in the beginning for the first block, right? So to start with, because it's a block which is going to be from 0 to k minus 1, right? So if you look at here, let's say a few elements. Suppose there is 5 here and 3 and minus 2 and like 9 and 7, something like this. So there are 5 elements here, and k equal to 5 in this case here. So this should be 4, index 4. So the max up to this place is going to be 5 here now, because that is the line where this is line number 80 here. In this for loop, I'm finding max up to sorry, in this case max from, right? So max from the position 4 is going to be 5, but max from position 3 is going to be 3 and 5. The max of that is still 5, and max from 2 is going to be still 5, but max from 1 is going to be 9, and then this is also 9. So this is what we are going to compute here, right? And so the max from 0 is going to be the max of the next k elements in this case. That's why I'm basically noting down here max from 0 is going to be my first result, because that is the first window, right? Starts at 0. And max up to is something I need when this begin index is begin of the window is not a mod mod k equal to 0 value. So I have some I'm initializing it to some int min. Let's see how it is useful. So whenever the begin of the window is mod k of that is 0, that means we are in a new block. When we are in a new block, I need to rerun this one. This actually I did it for the first time, but whenever this begin actually touches the next value is k or 2k or 3k, something like that, I need to recompute. This is where I'm recomputing it, right? So these 4 lines are going to do that. And max up to, I'll reset every time to int min whenever I'm at mod k 0, right? But otherwise, if I'm not at mod k 0, that means in that case, suppose when k begin equal to 1, I need this max of this which is available here, and also there is an element here. What if the next element here is say 10? So that is one element I need to keep track of, right? So this is where I'm doing it. So if in all other cases, the previous max up to and the current element which is the end of the window. If begin is the index of the begin of the window, if I add k minus 1 to that, it's going to be the last element of the window. So that I'm going to consider and find max up to, right? So this line number 23 is going to reset that max up to every time, right? So that it's only up to, but from beginning of that particular block, right? So that way I computed everything, and then this is just one line where I'm going to take the max up to sorry, max from the begin of in that block up to the end of the block, and then the max up to in the next block, right? Because the begin could be in the previous block, right? So this is going to find the max of the whole window, right? So if you observe here, what we have done in this case, the amount of time it takes is this whole thing is linear time, so big of n time, and along inside here, this, if you consider pushback is as a constant time, so it's kind of a constant time for this one overall. But inside here there is a for loop, but this is look at this runs for maybe big of k time. But this particular if then block within the if here is going to execute once per every k instructions, right? Or once per every k iterations, because whenever the mod k is 0, we only execute that, right? So that means the inside of the for loop runs for overall big of n time, right? Not more than, it's not like we need to multiply k. All right. So that's why the overall time it takes is linear time big of n, and amount of space we take is only for this much, this one, which is max from, which is a simple array which has k elements there, right? That's why this whole thing is going to take big of n time and big of k extra space, right? And this is the lower bound for this problem, and so this should be the most efficient solution, at least asymptotically, right? So it has accepted. Let's see how much time it takes, right? So yeah, it took 356 milliseconds and 105 MB. Looks like this is kind of not towards the top, right? 80 percentile is pretty good, and space wise, it's pretty good again. 94 percentile is also good. So this is one of the fastest way of doing it, and asymptotically, this is obviously the optimal solution we have, right? So there are actually multiple ways of implementing it. You can use Heap also. That is actually a more natural data structure to use, but it won't be this good, right? Even if you use a sorry, Heap, it's going to take big of n log k time. So that big of n log k is the solution whenever you use some kind of container, which takes log n time to update the container. That's gonna take big of n log k time. If you want linear, this kind of trick is useful. All right. So if you implement it in any other way, let me know. Otherwise, please like the video and subscribe to the channel. And thanks for watching.